row of mixed 1D tensor network states. So please start.
Yeah, thank you for introduction. So let's just start the talk. Yeah, so the outline of the talk, my talk is first I talk about some, the concept of generalized symmetry, which is, symmetry, but, beyond conventional group framework, group theory framework. And then it's deeply related to, especially in 1D systems, it's deeply related to the tensor network called matrix product operators. So I'll introduce this concept. And then I go more relation to more physical side, which is classification problem of 1D quantum mixed state phases, and then introduce density operators, which forms MPOs. And finally, I'll explain some main results contribute to this classification problem through some renormalization group flows for matrix product density operators. So generalized symmetries are, recently a hot topic in condensed matter physics, especially. So there are two types of kind of how generalized those symmetries. One is so-called higher form symmetries. Those are symmetries acting on subsystems rather than acting on whole systems. And usually people say it is K-form symmetry in D-dimensional systems, meaning that the symmetry operator acting on only D minus K dimensional subsystems. For example, if K is 0, then D minus K is just D. So in this case, the symmetry action covers whole systems, especially in this literature, the zero form symmetry usually refers to the tensor product symmetry. So each spin, so we are considering spin systems, by the way. So each spin is acted by some unitary representation UZ, and then the whole action is just a tensor product of them. And then one form symmetry, for example, in two-dimensional systems is a one-dimensional object, meaning that in this, this picture, the symmetry acts on some loop-like structure or line-like structures. These symmetry is sometimes very important to analyze, for example, subsystem SPT phases or topological ordered phases with Wilson loop operators. Another type of generalized symmetry is the mathematical structure behind the symmetry is kind of extended from a group theory to more general mathematical theory. Especially in this literature, lots of people are considering categorical symmetries. So those are symmetries described by certain category theories. And those symmetries play really crucial roles, again, in topologically ordered phases and also conformal field theories. And especially in these phases or theories, those categories, particularly in they are monoidal fusion categories. So after that, we are only consider monoidal fusion categories symmetries. So I don't go too much detail into the definition of fusion category or other mathematical structure because they are too kind of abstract and hard to explain in this short-term talks. So but anyway, so the category is kind of abstract, but they have a rigid algebraic structure by this theorem. So for any finite fusion category C, it is known that there exists a weak hop algebra. This is another kind of algebraic concept. We will abbreviate it in WHA and such that the fusion category is equivalent to some representation category of the hop algebra. So in this sense, fusion categories and weak hop algebras are kind of the same concept, but a different aspect. And again, weak hop definition, precise definition of weak hop algebra is really long, and not all of them are important in this talk. So I only mentioned that the hop algebra has a kind of bi-algebraic structure, meaning that it is algebra in the usual product sense. So if you have two operators, x and y, then we have a product xy, and it is hop algebra is closed under this product. and the product, satisfy usual associativity. And it also has a unit which commute with any operator, and product is always back to the original operator. And additional structure is a coproduct denoted by delta, and delta is somehow a dual of product. And this is a map, linear map from the algebra to the tensor copy of the algebra, and satisfying another kind of associativity relation. And this coproduct also has a kind of unit, analog of unit called co-unit. This is a map from algebra to some number satisfying. So if you apply some coproduct to some operator, after that you just apply co-unit to one of the subsystems, then you get the original state. So in this sense, one can see that coproduct must distribute information of the input to two copies of H in kind of equal way, so that you can always recover the original operator by applying co-unit on either first subsystem, first copy or the second copy. So these Hopper algebraic structure are actually related to the concept of tensor networks. And in 1D systems, generalized symmetry described by those algebraic structures are typically represented by matrix product operator. These are operators acting on many body quantum systems, and the coefficients of the expanded in product basis are written in this way, where Mij's are just D times D matrices, and large D is just constant in this talk. And for each Ij, there is one matrix. So if we change the index I or j, then we get another matrix. And the coefficient is given by a product of these matrices and then taking the trace. So that's why it's called matrix product operator. So this this kind of operator have some nice graphical representation. So in conventional tensor network literature, people denote tensors as some circle or boxes with legs, and each leg corresponds to the index of the tensor. For example, this AB picture, we have some 3-leg tensor A and 2-leg tensor B. And A has 3 index, and if we specify every index, then we get some number. And this connected leg between A and B means that the index corresponding to that connected edge is summed up. So in this case, B can be regarded as some vector with label J, and A can be regarded as a matrix with label I. And this picture means that the vector B is, so matrix A is applied to the vector B. So by using this tensor network representation, this MPO tensor network can be graphically written in this way. Here we denote the vertical leg as black. Those are physical indices, and those red line is a virtual kind of horizontal legs, and they are just used to taking sums. So each tensor component of MPO have 4 legs, and they can be represented in 2 ways. So it can be regarded as a matrix acting on those red indices by fixing the black indices. Vice versa, we can fix red legs and then regard it as a matrix acting on the black index. So technically, it can be represented by a tensor product of 2 kind of operators, and some of them. And left tensor factor meaning is the operator on the physical systems, and right tensor factor is operator acting on the virtual degrees of freedom. By doing so, this kind of connected tensor can be represented by this way, MM. Here, the product structure of left factor and right factors are different. So for physical factors, by looking this, we have independent four black legs, meaning that those legs are, taken tensor product. But that index is just connected, and then you have to take the sum. So in this case, the right-hand side, we have a matrix product, usual matrix product. But anyway, by introducing this kind of two factors with different product rules, we can simply write this tensor factor in one huge matrix. And this MPO is kind of related to weak Hopper algebra, mathematical structure behind the symmetry. So there is a theorem that saying any weak Hopper algebra can be represented by certain MPO algebra. That is just algebra formed by some MPOs with the same bond dimension. So suppose we have choose some injective representation of Hopper algebra, and also injective representation of the dual of the Hopper algebra. And by some simple calculation, we can see that the dual space as a just dual vector space of Hopper algebra is always weak. Weak Hopper algebra is always weak Hopper algebra too. So we choose psi as a algebraic representation of H star. Then we introduce some tensor from these Hopper algebra and representations by this way, where pi x is just acting on they are representation of H, and psi fx is a representation of H star. And we just take the sum over the basis. Here fx is just a dual basis of the original Hopper algebra. By doing so, we can, for example, calculate the connected tensor, and by using some simple algebraic relation, something like this in Hopper algebra, then we can see that this connected tensor can be represented by a tensor product of representations and co-product, and again another representation. So it has nice algebraic structure. And then for any x in Hopper algebra, let Bx be a matrix satisfying this relation. So F is an element of the dual space, so it is just a function. So we choose Bx so that if we take the trace with this representation of F as a matrix, then we get the function. So this is just matrix representation of psi f and its action to matrix space. So we can always find such matrix. Then consider tensor network something like this. So this is not just m's, but additionally we insert the matrix at the end of the boundary, and then taking the trace on the red legs. So then we get, by simple calculation, what we see is that we end up operator forms this red pi tensor n and delta power n minus 1. So this operator has nice MPO representation, and also it has a nice algebraic representation. And also this structure, this obtained MPO have a algebraic structure, meaning that it is vector space, and also if you take the product, because delta and pi are now kind of multiplicative by simple assumption, we can obtain if you take the product of these MPOs, then what we get is another MPO, but with a different boundary condition, and the boundary condition is just the product, boundary condition for the product. And this holds for any, length n. So they have a nice, MPO algebra representation as a algebra. So in this way, we summarize the first part. So what we have is, fusion category or almost equivalently, we call algebra, characterizing some generalized symmetry in some systems. And then for if they are acting on some one-dimensional systems, then we can always construct MPO algebra by choosing some pi and psi. These are injective representations of the Hopper algebra. So we can describe the physical action of such abstract symmetry by those MPOs. So the next part, I explain some more relation to how those mathematical concepts are related to some another physical problems. So recently, there are some reasons why people are interested in this kind of MPO representation of the generalized symmetry, because there is now people are interested in new classification of quantum phases, so-called quantum mixed state phases. We say this is a class of some mixed state, not pure state, but mixed state, that are connected by short depth circuit of quantum channels. Here, I just say, quantum channel is just CPTP map mathematically. So more precisely, suppose we have a rho 1 and rho 2. Those are some physically reasonable mixed states, so some mixed state in some physical systems. And we say these two mixed states are in the same quantum phase if there exists a short depth circuit of quantum channels converting rho 1 to rho 2 in this way. So circuit means, the layer of tensor product of local channels, such that there is another local circuit of quantum channel, which also converts rho 2 to rho 1. So there's two directional conversion. That's why we say these two are in the same phase. So this relation defines some kind of equivalence relationship between mixed states, and we have some equivalence classes in some many-body systems. And those equivalence classes are called, quantum mixed state phases. And to discuss more about this kind of classification, we have to specify the set of mixed state we want to classify. And the idea behind this is, in pure state case, we usually consider so-called gapped ground states. Those are ground states of Hamiltonian with energy gap. And they have a nice, well-behaved property, and they have a nice classification in terms of so-called topologically ordered phases. So we want to have a similar family of mixed state which have a similar property. And to do so, we focus on that, gapped ground states satisfy so-called area law of entanglement entropy. So entanglement entropy is just, amount of entanglement between some region to outside. And the area law says that the entanglement is always bounded by the size of the boundary of the region. So this kind of limits amount of entanglement and restricts the state to be kind of physically realizable, not just mathematical things. So for mixed states, the entanglement entropy is no longer a good measure of entanglement. So we can use the mutual information to quantify not only entanglement, but also classical correlations. So the amount of correlation, total correlation, can be measured by mutual information. So we can consider area law of mutual information for mixed state. Then this matrix product density operators, in short MPDOs, appears because these are a natural tensor network for 1D mixed states and satisfying area law of mutual information. almost by definition. And they are actually good answers for example, quantum give states. So, these are, sufficiently physical. And also, these MPDOs include not only just thermal state, but more complicated state. And they are related to 2D physics again. So PEPS is 2D pure state tensor networks, and MPDOs can appear by taking some patch of PEPS and taking partial trace on the physical indices and remaining these virtual legs. And then what we get is some 1D mixed state along the boundary. In this construction, we can always construct D-1 dimensional mixed state from D-dimensional pure states. And typically, if large D is two-dimensional case, then the boundary mixed state can be described by MPDOs if the pure state is gapped quantum phases. And for example, if you choose the D-dimensional original pure state as non-trivial as possible, just like 2D topological order, then what we obtain some MPDO at the boundary, which is beyond the conventional thermal structure. So we can classify. We want to classify these phases, and we focus on denormalization fixed points to do so because they have a simple structure. So for MPDOs, it is in 2018, it is proposed that MPDO is called fixed point MPDO if there is a pair of CPTP maps which maps one site to two sites and two sites to one site reversibly. So we can freely increase the number of sites and also vice versa. By introducing this fixed point MPDO, there is nice structure, meaning that any MPDO satisfying this denormalized fixed point condition can be decomposed in this way. So there is some global MPDO part and commuting give state. But the original paper didn't say anything about this global MPO, how are they structured. But recent hint is that any weak Hopper algebra, we can construct denormalization fixed point MPDOs with this PIs described by weak Hopper algebra symmetry. So we can kind of guess that this any fixed point of MPDO can be decomposed into some weak Hopper algebra symmetry part and commuting give state part. So for the time reason, I just skip this. But anyway, the motivation is that if all the fixed point or all the MPDOs are characterized by this kind of weak Hopper algebra framework or not. Yeah. Then, for example, some example is double semion boundary. This is some yeah, we have some so-called double semion topological order in 2D systems with some, characterized by some fusion category with Z to omega. The boundary state is some MPDO with this Hopper algebra structure. So this is the Hopper algebra is, as an algebra, it is just, direct sum of 2x2 matrix of algebra. But they have an additional structure, coproduct structure defined in this way where omega is some so-called, third cohomology or something. And they also have a co-unit and satisfying all axioms of weak Hopper algebra. So this is somehow non-trivial 1D MPDO. And it is shown that this Hopper algebra, weak Hopper algebra, generates some family of fixed point MPDO, which is in the first example of non-trivial quantum mixed phase. Yeah. So this is a very important example in this classification problem. Although this looks kind of messy. And our contribution is, so far we have considered, the direction from algebra to operators. But we complete the characterization, we want to do some backward thing. So we want to extract some algebraic structure from given MPO to check every, to classify every possible MPDOs. Again, so the problem is, the exact renormalization structure. So we have considered, a renormalization fixed point, but in general, we should have some, for given MPDO, we should have some renormalization flow going to that fixed point, some certain fixed point. But the existence is kind of non-trivial problem because in the case of MPDOs, they are mixed states. So, renormalization flow is some CPTP maps and they are not generally reversible. So desired exact renormalization flow is something like this. So we have some tensor network in 1D and we, by applying some renormalization procedure, we can, compress the subsystem into some smaller dimensional systems so that the dimension, at the end, the dimension is independent of the original size and to make sure this flow converges. And also we have to make sure always we can back to the original state to guarantee the phase is somehow unchanged under this exact renormalization flow. Yeah. And to do so, we have to check how much you can compress the tensor network. And I used some technique of the Quasi-Imoto decomposition, well known in quantum information theory. This is a decomposition, well-known decomposition of quantum bipartite state. And we can apply this decomposition to part of tensor networks to get this kind of direct sum decomposition. And what we see is that that index only, connected to the WA blocks and omega A blocks are just, tensor factors and not related to Z indices, which means the correlation is not, not contained in this omega. So we can just discard this part, and then we can reduce the dimension of the physical system. And we show that this is the optimal strategy, and you cannot, compress much more by keeping the reversibility. However, by checking this minimum dimension, we found that there are some MPDOs does not have a converging RG flow. This is an example on Q-trip spin chain, where the large lambda is just diagonal. So this is purely classical MPDO. The point is this large lambda has 3 eigenvalues which are distinct. Then by checking how much dimension you can compress by this RG flow, then what we see is that the dimension is determined by the number of different eigenvalue of lambda tensor L, which grows actually with respect to the original length of B. So you cannot, have a converging RG flow for this kind of MPDOs, unfortunately. This is mainly because of the exactness of the recoverability condition. So somehow we need to consider RG flow for this kind of MPDOs. We need to consider approximate compression. So because we want to first classify those MPDOs with RG flows, we need to introduce some subclass of MPDOs to guarantee there is nice exact RG flow. So to do so, we first focus on the Quasi-Imoto decomposition of the tensor for length L tensor. Then we define some algebra spanned by this matrices on this crucial block. So this omega block is kind of irrelevant for this RG flow, so we just ignore this. And then we get these sub blocks of the matrices. Then we consider some algebra spanned by these matrices. And Then the first condition is that to guarantee that the RG flow always converges, we have to make sure this dimension is always can be chosen to be constant. So this is the first condition. So for any length L, when we decompose into this way, this left block has always constant dimensional size. So this is the first condition. Mathematically, there is some more complicated statement, but intuitively it just says this is constant. Yeah. By defining this kind of algebra, then spanned by the W blocks, then what we get is somehow some operator, some map from A to product of a tensor A. So by decomposing some region B into two parts, what we have is the direct sum decomposition here, the whole system and each subsystems are related in this way. So you can always get smaller algebra by decomposing the whole structure because we can have more operations. So this is subalgebra of this tensor product. And then we find there exists some kind of map delta from this guy to this tensor product through this commutative relation. Now we say this L is just representation of some constant dimensional algebra, and then again we have a delta L1 plus L2. But we assume that this L1 plus L2 is irrelevant. So meaning that this delta is always fixed map from A to A tensor A. Then what we see is some linear map from A to A tensor A. So you see that this really looks like coproduct I introduced before. And actually, I can show that this linear map constructed this way under these two conditions satisfy this associativity relation. So this is actually a co-multiplication. So we can obtain some co-multiplication structure from RG flow conditions. Moreover, this delta satisfies this multiplicativity relation. It is also required for Hopper algebra. So there are different family of algebra and bialgebra stuffs. So if the algebra is unitary algebra and also have a co-unitary coalgebra structure and also have this multiplicative relation, then the algebra is called pre-bialgebra. And there are relations between weak bialgebra and weak Hopper algebra, something like this. So roughly speaking, pre-bialgebra is the most generous stuff. And then by setting additional structure, it is called weak bialgebra. Then further assuming some additional structure, we get weak Hopper algebra, which is related to generalized symmetry in quantum phases. And Hopper algebra is just a special version of weak Hopper algebra. So we have some structure preliminary to weak Hopper algebra. For example, the simple example is boundary state of toric code, and then we can put some noise parameter PL to make sure it is not renormalization fixed point. But by using our proposed methodology, we can extract some algebraic structure, and then we can find the algebra is actually C2, and we can find actual this product from this state MPO, and we can also further co-unit, and then long story in short, we have some kind of renormalization flow diagram here. So it is nice. Another example is this mixed dimer state, but this I just skip this. This is just a tensor product of bipartite mixed state. But even if the state is such simple structure, we found that corresponding algebra have a co-multiplication, but does not have a co-unit. So it kind of conflicts the weak hop algebra framework. Another example we found recently is CZY state. It is defined by in this way. So this is just sum of identity and this unitary, which is somehow entangled in whole systems. So CZ get creates some entanglement, and YZ is just local Pauli. This is written in some simple MPO form. And we can extract algebra structure again by using our proposed method. And what we get is direct sum of 2x2 matrices with this complicated coproduct structure. And we again find that this coproduct structure cannot have a counit. And we see that this direct sum, matrix algebra before, which is double semion boundary state. And actually, these two states are really related. So they have a CZY state and double semion boundary state have exactly the same algebraic structure. And the double semion boundary state is related to fusion category classification, and they have a counital coproduct and satisfy all the axioms of weak hop algebra. So they are, this is nice. H is nice algebra. But the algebra we found for CZY state have a no counit. And also the corresponding category theory is semi-monoidal category, not a fusion category. So, they don't have a nice kind of properties so far. However, we found that actually these two, algebras are connected by some, constant depth quantum circuit. So actually as a phase, quantum mixed phase, they are in the same phase. So let me summarize my talk. So we introduced some exact algebra flow condition for 1D mixed state to extract some algebraic structure from given tensor networks. So this is kind of opposite approach from the conventional from algebra to tensor network approach. Then we extract some algebraic structure for various examples, and we found that sometimes this algebraic structure does not have a counit. So they don't have a nice position in conventional weak hop algebra framework. However, sometimes even they have a no counit, they somehow belongs to the same phase as the weak hop algebra framework. So open question is how to formulate, approximate algebra to include more every MPDOs, not, removing the, we want to remove the additional condition for exact algebra flow. So to do so, we need approximate algebra, but we don't know how to do so. And the second question is how can we classify coproducts in the same phase? So this, we found two algebras can have a different coproduct structure, but in the same phase. So we want to find how they are related. This kind of relation seems to be beyond the usual, relationship between hop algebra theory because they usually keep counit. So that's all for my talk. Thank you.
Thank you very much. So from Nagoya side, is there any question, comment? From Shenzhen or from Zoom, is there any comment or question?
So sorry, quite difficult for me. So, because I'm not so familiar about the area law. So, but looks like this is fusion category. Fusion category also discussed by maybe that guy, Kon Liang. So, is there any relation with Kon Liang's talk?
Oh, yeah. So fusion category is usually used to describe 2D ground state phases, topologically ordered phases, or topological quantum field theory. Conventionally, they are used in such literature. But recently, people now interested in boundary of such 2D pure systems. And the boundary is 1D and also mixed. So now people are interested in again, the boundary have a same mathematical structure, or if there is a gap, yeah, that's the kind of relation. But the gap is still unknown. So maybe every 1D mixed state is also described by the same mathematical structure as 2D TTUFT, but maybe not.
And also, looks like that's kind of advanced concept more related to mathematical physics. So, how about how mathematical physics guy in Nagoya consider that topic? So,
Well, I have a few questions. So can I ask?
Yeah, okay.
Yeah. And yeah, could you show me the last slide?
This one.
This one, yes. And yeah, very interesting point is that so you have two algebras, H and A.
Yeah.
Yeah, and so algebraically they are different, and corresponding categories are also different. But the last statement says that
Yeah, so actually, so these are mathematical structure behind physical density matrix.
yes.
And the last statement is the physical states are actually two physical states are in the same mixed state quantum phase. And what people believe is that this kind of algebraic structure somehow contain information about phase. So we kind of expect somehow these H and A have some common property related to that's characterizing the same phase. But we don't know how to characterize the common property because these two are kind of complex structure are so different, so that we cannot apply usual, for example, Dirichlet twist or something because one has no coproduct, co-unit. Yeah.
So anyway, so as a monoidal categories, they are different.
They are different.
So the second one is not monoidal, maybe semi-monoidal.
Yeah, because they don't have a unit, co-unit.
So yeah, on that point, I have some feeling. So in mathematics, it is there is well-known technique to put or add co-unit by hand.
Oh yeah, unitarization. Yes.
And is a similar technique can be applied to this setting?
We have tried some, analysis, but somehow they are not directly related. Some problem is this relation, physical map from one to the other, it includes shift. So translation of one spin to, every spin, moving every spin to one step in the right. Translational shift. And it is kind of hard to, hard to describe locally. They always global properties. So it affects to the coproduct structure very non-trivial way.
But maybe this is very interesting if one could somehow mathematically formulate that global shift.
Yeah. Thank you for the question.
Thank you very much. Is there any other question or comment? Then let us thank Kato-san again.
Thank you.
And the next speaker is also from Nagoya. And please wait a moment. Just right. そっか。そうなんだ。話か。Yes, let's start the next talk. The speaker is Kwan Jiangxi-san from Nagoya, and the title is The State Refocusing Square Root Instrument and Retrodictive Entropy Uncertainty Relations. So please start.
Sorry, I cannot hear anything.
Can you hear me?
Yes, now.
Oh, okay, sorry. So let me like introduce again about my background. So first of all, the quantum measurement shows one of the main differences between the classical and quantum physics. And the general quantum measurement is always represented as positive operator value measurement, which is also called as POVM. And in quantum information theory, the measurement process can also be expressed by a quantum instrument. In the study of the quantum measurement, one of the most important topic is the study of uncertainty relations, which has been studied extensively these days. And start from a special kind of quantum instrument that we call the state refocusing square root instrument. So in short, the SR instrument. We focus on its properties and its possible applications on the uncertainty relations. So first of all, it is a brief introduction about the definition of POVM. So it basically is a set of several positive operators with the classical outcome index X, such that they are all like positive operators, and they sum up to a identity which coincide to the probability distribution, the PRX, according to the Born rule, which is the trace of the MX law if you are given a density matrix law. And then now we know the operator of a measurement, but we want to we want to embed it into a quantum channel so that we can like analyze the information flow of the quantum measurement. So that's why we need this this concept of quantum instrument. So the quantum instrument is a collection of some trace non-increasing map. It is CP but TNI map, and the sum of them is trace preserving, corresponding to a given POVM, such that the trace of each member of the quantum instrument is equal to the trace of the POVM elements. So the above implies that the implies that we can consider this quantum instrument as in this form, in this summation form. So where this x index is an orthonormal basis and labeling the critical output of the instrument. And so for the ease of analyzing, we need to like the cross representation is always used to express a CPTP map.
Again, I cannot hear. Sorry, I cannot hear now. Maybe some problem in our side, I think.
Yes, maybe
Sorry,
the battery has running out. Sorry. So for the ease of the analysis of the CPTP map, we need the we need a cross representation, which you can always say that a CPTP map can be represented in a summation of a like the the sandwich form of a cross representation, where the ki are so-called cross operators, and the summa of the cross operators like the dark line itself coincide to a identity. Then we introduce the most efficient way to construct a quantum instrument, which is so-called the square root instrument. Is defined it as this form by just easily setting that the cross operator as a square root of mx. Also, you must know that there is also a classical side of that, but we for in short, intuitively, we can just understand that the cross operator is the square root of mx, and there is no. So basically, this like if you consider the ki as square root mx, the summation is coincide with the identity. So okay. Notice that in general, one can always do the post-processing with a unitary UX for each outcome X after the quantum instrument and do not bother the measurement outcome. So such that we can write it into this form. I call it like I am here now. So applying this UX, we consider the polar decomposition of this square root of low and square root of mx. One can always find a unique unitary matrix, which is dependent on the mx and the low to make this whole thing as in this form. So which means that we can if you look at that, like consider this ux square root mx low square root mx as a like separated into two parts, like square root and square root. This whole thing is like defining the ux as ux low and just combining together. So which means that we can write the instrument in the quantum part of the outcome of the instrument in this form, which is square root low mx square root low equals to the ux low mx this form. So therefore, by choosing the proper unitary ux low, which is based on the state and the measurement, we have the state refocusing square root instrument. So which is showing it in the below of this slide. So what is the use of this SRSR instrument? So let's analyze some properties about this instrument. So first of all, it has the correlation. It is correlated to the path transpose map. So as you know, like 2 days ago, like it's already been talking by Professor Francisco Buscemi. So the well-known path transpose map is defined in in this form. And now, for the SRSI instrument, defining it before, we define the corresponding quantum classical channel as this form. So basically, you can see that you are tracing out the quantum part and of our SRSI instrument, and you will get this channel. So one can easily see that where. So for each outcome, x0, and let the E here defined in the path transpose map is this measurement QC measurement channel M, and omega is so the state is given as the x0, and set the prior state gamma as low. We can get the output of the path transpose map as is the square root low mx0 square root low and divided by some factors to normalize it. So to calculate this m daga, one can just consider the cross operator m is the ki xi square root mx. We found that the output of the path transpose map R low m for one output information is the normalized state of the quantum part of the output state of our SRSI instrument. So the question is, what does the path transpose map mean? So this is also introduced by Professor Bishimi. It is related to the quantum-based root and therefore the retradiction. So I will explain it again for the ease of the understanding. So we define two bipartite states, which is defined in this star things E star low as the like how to say, as a channel to the state. It is equal to the identity of outcome and the low the transpose, where the CE here is the Choi operator of the channel E, and we define the Q. We define the reverse channel, Q reverse, in this form also. Notice that this transpose is just for like coincide these two bipartite states form. So basically, after the transpose, you can see that all these states coincide together. So the out is out, in is in, and the transpose is also keep transpose. So with the preparation of the definition, we can now construct the quantum minimal change principle. So the classical bias rule can be derived from the classical minimal change principle. Recently, the quantum minimal change principle is defined by this paper, which is also written by the Baigel and Francesco Buscemi and Varel Scarani, and be used to derive the quantum-based rule, which is basically a optimal problem or optimal program. So choosing the maximized fidelity of these two bipartite states subject to the this reverse channel is a CPTB map, where the fidelity F low sigma is defined as the traditional form. And with that, we can say we can now consider the quantum-based rule. So basically, the optimal solution of that of the quantum minimal change principle is basically is this channel subject to this form. And furthermore, if this the outcome information tau and sigma gamma is commute, then the solution coincides with the quantum transpose map, with the path transpose map. So notice that then the forward channel E is a POVM QC channel, then the reference output tau is the classical information And then we can we got from the POVN, so that we can easily get that in a quantum measurement channel, this tau and E gamma is basically commute. So for the quantum instrument, the quantum base rule coincide with the path transpose map. Now we can say that this is exactly the state update route based on the classical information X. So as discussed before, our SRSI instrument output the subnormalized retrodictive update states after the POVN for each classical output X. So this figure is for ease of understanding. So basically you input with a state to this big square is our SRSI instrument, and we use the information of each classical X throughout this and the information of rho to control this unitary. And here is basically a simple square root instrument. And what we get from the outcome is this square root low mx0, square root low, and the classical outcome x0, x0. So this x0, x0 is what we can actually see in the measurement, I forgot the word. I forgot how to say the word. So actually from this instrument, we can just consider using this classical. You can use this classical information to retrodict the state. Another properties about the SRSI instrument is correlated to the uncertainty principle, uncertainty relations. So first of all, let me explain about the sequential measurement. So based on our SRSI instrument on the first measurement, one can consider following sequential measurement of these two POVM. So, but these two POVM can be the same. So you can see the form here. And an interesting observation is that consider using SRSI instruments, the joint probability does not change, even swap the order of the measurement. So we can see that the joint probability of the X and Y coincide if we swap the order of M and X and Y. But remember, we need to keep the first measurement to use the SRSI instrument form. And the marginal is also correct. So this make us thinking about the how about using this sequential measurement channel to consider a uncertainty principle. So basically, one can see that for the joint probability distribution, we can see the probability itself, probability distribution itself is in this form and is in a really beautiful form of this norm 2 square of the square ny square low square mx, and that's why we can conclude that the state-dependent entropy relation 1 is that the entropy of the hx low plus hxy is larger than this one, and it is larger than the minus max this form. So compared to the famous Mason-Wolfing entropy uncertainty bound, we can see that the only change is that we add the square root low between this mx and my, and we use the norm 2, but not this norm infinity. So our bound may be useful for the entropy uncertainty principle. And so the second relation is the consider that the sequential measurements channel is CPTP and subunital. So we can just consider the bound of this one, where the IGO is the gainable information, information. Just a little bit forgot how to pronounce this thing. So basically, this IGO is defined as this. And the low tilde here is defined as the just putting the daga of this instrument after the measurement. So note that this daga map, this diagram map is trace non-increasing, so the low tilde is subnormalized. And since this inequality of the Umegaki relative entropy, the use of the low tilde actually makes the bond tighter. So assume now we use we set the two POEMs are both rank 1 POEM. In this case, this IGO is equal to the entropy of the state. So we can have the another entropy uncertainty relation, which is larger than this one. We did some numerical tests compared to our bounds and Mason-Wiefink's bound. We found that our bound is tighter when the dimension is larger than 3 and the number of the elements of POEMs both larger than 3. But when the D is 2 and N is 2, it seems that our bound and theirs bound. So here I write Berta's bound because we used the, I forgot to change this thing. And here is the numerical outcome. Here you can see. So let me conclude my presentation. So the first future work should be open question is the interpretation of the retrojective uncertainty relations. So based on the apple-based idea, the retrojective error is defined as the error between the initial observable system and the output measurement pointer. However, from the quantum-based route, the information that has been retrodicted is the state itself. So therefore, the retrojective error becomes the guessing probability of the initial state. And interestingly, we found that the observational entropy is actually talking something about the recoverability of the original state based on the talk of the Professor Buscemi. And we're also working on the analytical proof of the tight bond because we only have some numerical tests so far. So we need to do some analytical proof in the future. So, okay, that's all of my talk. Thank you.
Thank you very much. From Nagoya side, is a question or comment? Yes, we have one.
Thank you for the talk. So is there any possible application for like estimating more like the property of the system, like parameter estimation or anything?
I think because it is you use the SRSR instrument, you restrict the information about the state itself. You can actually have some. So basically, because you like you have restrict the whole information of the state itself, you can get some other parameters from the after the restrict.
But to do so, you have to construct the SRSR instrument first, right?
Sorry.
You have to construct the instrument first, and
yes. So that's why if you consider here. So if you consider back to this path transforms map, and if you set this prior from low to like the U, which is the uniform state, you will see that this whole thing becomes to the mx0 divided by the trace of the mx0, and it is basically coincide with the what we say the observational state that the Professor Buscemi has talked 2 days ago. So my consideration is like even though we don't know this square root of low, we can still by assuming assuming from the
prior,
yes,
uniform prior,
yes,
and then
uniform
update.
prior, and then you can use the update form as
Yeah. Okay.
yeah.
Thank you.
Then from Shenzhen or Zoom, is there any?
Hello. I think I in many years ago I introduced this kind of a square root instrument in my textbook. So did you check my book?
This square root instrument We have do some research about how the origin of this thing, and we found that it is from the paper from Fuchs. But I'm sorry, we didn't like found the square root instrument in your book.
But truly, I write down this one. So, for example, any how to say instrument can be written as application of this square root instrument plus TPCP map depend on the outcome X. So any instrument can be written by using this one.
You mean
example.
you mean this square root instrument form?
No. Any instrument can be written by using this square root measurement, square root instrument, and for TPCP map depend on X. So in that way, we can consider that any measurement can be written with this form. Can you understand? For example, so I discussed this one in my book. But of course, you didn't discuss this one. So
Do you mean I'm not very understand. Do you mean the square root instrument or the state refocusing square root instrument? Because here,
not this one.
not this one.
Not this one. So general. For example, there is a instrument and P of M. This is not one-to-one correspondence. So for instrument, you can find the P of M, corresponding P of M, but the instrument is not unique to corresponding to the P of M. Okay?
Yes.
So in that case, so there are so many kind of the instrument corresponding to the one P of M, but in that case, any that kind of instrument can be written by using this square root instrument and plus TPCP map.
Yes. Of course.
But that kind of statement, for example, proved in my book. This one is the first time, I think. So several things discussed in my book. So please check this one.
Okay. Thank you very much.
Other comment? No. Then let's turn the speaker again. And the next talk by Hayashi Sensei will start on schedule.
But too early, I think. So what time now? What is 27? But my talk from from 13. So 27, 3 minutes. I think you can this hard.
Yes, we see.
多分。本当 Can you see this hand?
Yes.
Okay. Oh, that's nice.
Yeah, I can see from your screen.
Okay, that's nice. Mm. Also, also broke, no? Don't correct. Yeah, that's not correct.
So let's start the final talk of this morning session. The speaker is Hayashi Sensei, Professor Masada
Okay.
Hayashi, Chinese University of Hong Kong, Shenzhen, International Quantum Academy in Shenzhen, and Nagoya University. The title is Heisenberg Scaling based on population coding. So please start. Hayashi Sensei, maybe the mic is off. We cannot hear you. Hayashi Sensei, can you hear me? And we cannot hear your voice.
Hello, I think now time, I think.
Yes. Can you hear my voice? No?
あれ Hello, 柳田さん。So,
sorry, I'm very sorry.
I think the time, already time. So, could you
Can you
start?
hear me? No.
Maybe. Can you hear me?
Yes, but you cannot hear my voice.
The system doesn't work. Hello.
Hello, can you hear me? No. No.
Could you answer now side?
Zoom 上は聞こえている?
Speaker doesn't work now in this side. Oh, なんか言ってる。ちょっとチャット。ああ。So they mentioned that Nagoya side can hear me, but maybe our side cannot hear them, I think.
We can try it again.
Eh?
Maybe we can't hear them now.
Could you speak Nagoya side? So maybe we need to check we can hear Nagoya side or not.
I'm now speaking.
Okay. Now we can hear. So
I see. Then I'm very sorry, but let us start the final talk of this morning session. The speaker is Professor Masahito Hayashi from of Chinese
This one,
from
okay.
Shenzhen,
Not to stand. So then I have to use here.
International
So-
Quantum Academy Shenzhen.
Sorry. Okay, please.
So let
So
us
can I
start.
start? So, okay, can I start?
Yes, please.
Okay, so now today I want to talk. Thank you for coming to this workshop. So today I want to talk about the our recent result. My recent result about the Heisenberg scaling based on the population coding. So this one is this. So usually, recently many people focus on the how to say Fisher information to describe the performance of the state estimation or unitary estimation, channel estimation. Of course, in the case of state estimation, Fisher information is very efficient. So Fisher information describe the performance of the estimation error. This one gives us some limitation in the case of state estimation. But in the case of channel estimation, there are some difficulty because to apply the performance of the estimation based on the Fisher information, we need several assumptions. So, for example, in the classical case, we need to assume IID condition independently identical distributed condition. This is quite essential. And in the case of state estimation, of course, we can repeat the same measurement, and also we make some, how to say, two-step method. So then local optimum measurement can be performed after the suitable two-step method. So then state Fisher information is okay to achieve that performance. But in the case of unitary estimation, sometimes people input the very strange state to optimize maximize the Fisher information. In that case, you can achieve the optimum Fisher information depend on the state, depend on the channel, so or depend on the unknown parameter. So due to that problem, so it is quite difficult to globally attain the optimal Fisher information. Due to that problem, so sometimes it is not so good to use the Fisher information as a figure of merit. To resolve that problem, sometimes people want to consider another figure of merit, but the problem of the Fisher information, that information only reflect on the only one point, so only local information reflected in the case of the Fisher information. To resolve that problem, we need to consider another figure of merit that need to reflect the global information. So how to discuss this one? So now my alternative proposal is the mutual information. Mutual information describe the global information. So for example, now we want to consider this kind of the state. This is the unknown state, or some we don't know that parameter theta, but we have some candidate of the theta. So this is usually the continuous value, and we have that classical state, and we have that player distribution. We consider that kind of classical quantum classical state. So sometimes this is classical and this is quantum. So that kind of joint state is quite important to describe our knowledge. So in that case, we have some mutual information between the system A and B. So this is A and the system, and this is B. So we consider that mutual information. That kind of mutual information calculated this way. So this is some average state, and S is the entropy, phenomenon entropy, and average state, and phenomenon entropy of the each state. So we discuss the phenomenon entropy and conditional mutual in phenomenon entropy. That difference is equal to the mutual information. So this quantity can be reflected on the information for the global sense. So of course, this is quite important to sometimes we employ the this quantity for the channel coding. So we want to consider this quantity. So in the case of this state, if n is very large, so in that case, we have this result, at least in the classical case. In the classical case, we have this behavior. So D is the number of parameters, and N is the size of a number of copies, and half of the number of parameter times log N. This is optimum. We have this behavior. So this is a very famous result in the classical case. This result derived by the, how to say, Clark and Baron. And sometimes we often discuss model selection. To discuss the model selection, sometimes people employ this quantity. So, so now we consider a D-dimensional system, and mu is invariant. So some reference show that this one. So this is quite important result. So of course we have this quantity. So now we want to consider the meaning of this one. So. And this one is result of full parameter model. Okay, sorry, mistake. This one is a full parameter model. So if we consider full parameter model, we have this one. So we consider full parameter model T-dimensional quantum system. So in that case, the number of parameter is T squared minus 1. Because now we have a quantum system and density matrix. In that case, density matrix has a parameter. The number of parameter is T squared minus 1. This is number of parameter for the full parameter model, and divided 2. We have this one. So this is the case that if the D equal to the T squared minus 1, still we have this one. So this one is the same result as this classical case. So this one is the state estimation case. So now also we want to consider the number of states. How many states can be distinguished? So this one is, of course, this is very common with how to say topic with the channel coding. So using the Fano inequality, this is very common method in the information theory. So in that case, we can calculate the number of distinguishable elements. So now we have n copy of states, and how many states, depending on theta, can be distinguished within epsilon error. If we want to consider this problem, so that number is bounded by this quantity. This one can be easily shown by the Fano inequality. So in this way, what we want to say, so this kind of number is closely related to mutual information. So in this sense, mutual information is quite important. And now we want to consider population coding. Population means that the in order to describe the information, we use the population. Population means that not the number of persons. So sometimes Japanese people consider that population means that, or many people consider that population means that number of person element or number of persons. But in this context, population means that how to say, a kind of an ensemble. But ensemble is not correct English. So how to explain this meaning? So in Japanese, this kind of population meaning the shudan. So I don't know how to explain the English. So so something like that. So many elements. So for example, population means that originally come from the concept of the neuroscience to describe some information inside of the brain. You cannot use only the one neuron. So there is several neurons. So to describe the one information, we need to consider collection of the neurons. So in this sense, sometimes we mention that this is population of the collection of the neuron in this context. So in this sense, so we have some n states. N state is a kind of the population. So using this population, we want to describe the parameter theta. This is a very common method in the neuroscience. So we want to considering the similar sense to discuss the state estimation, and we discuss the mutual information. So in this sense, based on the concept of the population coding, so how we want to consider how many states can be distinguished in this sense. Here, in this sense. So then next one is the general problem of the formulation. So previously we discussed the state estimation case. Of course, in the state estimation case, that's kind of the population coding is quite meaningful, and we can understand that that kind of mutual information describe the amount of the information, global information, instead of the Fisher information. So in the case of unitary estimation, we have a slightly different. F is a unitary matrix depending on G and sometimes state G. So sometimes we consider twirling operation. Twirling operation is the average with respect to the application of F, and we consider its average based on the mu. Mu is the Hall measure of the G. So sometimes G is a discrete group, but sometimes D is a Lie group, so continuous group. So, and we want to write down the set of all unitary representations, irreducible representations. That one is F hat G, and F is some specific representation, but inside of F, there are several irreducible representations. In that case, our representation written as in this way. So mu r u lambda is a irreducible representation, and lambda describes that's how to say lambda describes that's irreducible representation. But sometimes this kind of irreducible representation is not one inside of this representation. There are several multiplicity. So multiplicity described by in this way. So of course, usually you can write down the tensor direct some product many times with the same guy, but that description is not so efficient. To avoid that repetition, we want to write down in this way. So in this case, this n lambda is a number of repetition. So this is sometimes called multiplicity. So next one, but sometimes we use the this reference system. So because number of in order to make a unitary representation, sometimes we need so enough number of the multiplicity. But if the number of multiplicity is not enough, we need to add that reference system. So in that case, the totally we have L times n lambda multiplicity. So in this way, we can increase the number of multiplicity. Multiplicity is quite important for the unitary description, unitary discrimination. So in this case, but the fat number is quite important. In that case, even though this is so many, so this is not so useful. So fat number is required. We number equal to the dimension of this irreducible component, irreducible representation. This one is d lambda. So we often consider this minimum number, minimum of this one or this number. If this guy is greater than this one, so in that case, you don't need to increase this one. So in this case, it is enough to consider this number. So NL lambda is greater than D lambda. In that case, that extra part is not so important. So it is enough to consider this number. So now we consider that L is greater than this one. So in that case, this minimum equals D lambda. So in that case, we have this one. This is quite simple. And in that case, our discussion is enough. So in that case, what we have? So firstly, we want to discuss the mutual information between the A and B. But now we have a system A has a, how to say, reference system. So reference system, the dimension of reference system is L. So then we write down in this way. So sometimes we write down AR and B, and but AR is replaced by L. So because the dimension of the reference system is L, so we write down in this way. And P is now we want to consider mutual information, but P is what is P? P is the distribution or the choice of unitary. So G is the choice of group element. So then FG is a unitary. So then PG can be considered distribution of the unitary. So that's kind of the mutual information depends on the that kind of distribution. So and also that kind of mutual information depends on the initial state of rho. So we have two kind of the parameter P and rho. So in this case, mutual information write down in this way, and its upper bound is written as this one. This is relative entropy, and this is average guy. So in that case, that's mutual information is write down in this way. If the state is pure state, in that case, mutual information written as a phenomenon entropy of the output state. And so then our problem formulated as follows. So we want to maximize the mutual information. So how much you can obtain the large mutual information? In that case, we need to optimize the choice of input state psi and the choice of distribution of the P. Distribution P. So, but we can easily find that the optimum distribution is hard measure. This one is optimum. So in that case, we have a phenomenon entropy of the twirling of this guy. So then our problem is simplified to that maximization of the initial state psi, and we need to consider a phenomenon entropy of the twirling. So we need to consider this maximization problem. So this is not so difficult. So then that kind of problem can be written down in this way. So if the initial state has this form, psi lambda is a kind of the state, so optimal state, and this is a distribution of the superposition coefficient is P lambda. So in that case, phenomenon entropy written as this one, and P lambda is a projection to that state system. So then finally we write down this one, and we need to optimize the distribution of the P lambda. So finally, what we have, so that kind of mutual information is upper bounded by this guy. So log of the D lambda and the minimum of this guy. So if P lambda is choose that kind of coefficient P lambda choose in this way, so we have equality. So then this guy is the optimum value. So in this way, after optimizing the distribution and the initial state psi, optimum mutual information is this guy. So sometimes, of course, in that case, optimum state is this guy, but sometimes L is sufficiently large. So in that case, that minimum equal to D lambda. So the optimum value equal to this guy. So log of the square of the representation dimension of the representation. So we have this one. So this is in the next part we discuss the meaning of this guy. So in this case, the meaning of the population coding is how many parameters can be distinguished in the case of the population coding, so n-tensor product coding. So in that case, we want to discuss the distinguishable element. So in this case, we define this quantity. So this is the epsilon and this is the initial states. So how many states, how many parameters can be distinguished within epsilon error? So in that case, this kind of the this one is number of distinguishable elements depending on the input state law, but we optimize the choice of input state. So then we have this quantity. So finally, what we have, so if we have some input state psi, so in that case, we have upper bound and lower bound for the number of distinguishable elements. So lower bound for normal entropy, not for normal, no, this is linear entropy. I will explain this one later. So, and also linear entropy beta with this upper bound. So we have lower bound, upper bound in this way. and this additional coefficient part is not so big, quite small. So in particular, we choose some epsilon alpha or beta. So finally, we have this kind of the distinguishable element can be optimized in this one. So yes. RG is sorry, maybe this log is not needed. Sorry. So in this case, we have upper bound and lower bound for the number of distinguishable element in this way. So in this sense, almost same as calculation of the optimization of the mutual information. Once you can calculate the optimization of the mutual information, then we can evaluate the upper bound, lower bound with very small error. We evaluate this distinguishable element. So in this sense, it is enough to consider calculation of the mutual information. So this one is the justification of the measure of the mutual information. So then, in the next step, we want to calculate the number of distinguishable elements. So in the case of some special representation, so what is a special representation? Firstly, we want to consider quite a simple one. So we have only diagram element and we have a phase factor on the some diagram element. We want to consider multiple phase estimation. This one is quite a simple model. So in that case, we have we have a t-dimensional case, and the first system has no phase action, and another part has this EI theta j phase factor. So we want to estimate these t parameters. So in this case, we need to consider this kind of combinatorics. This combinatorics is quite important to describe the number of irreducible representations. So if we have an n-tensor product case, the number of irreducible representation inside the n-tensor product action, in that case, number of irreducible representation is described by this one. So this element, each element describes the one irreducible representation. So then the total of the number of irreducible representation can be written as this combinatorics quantity. This is combinatorics quantity. So then mutual information directly calculated to this one. So because this is a commutative group action, so then irreducible representation dimension is 1. So in that case, it is enough to consider the number of irreducible representation. So please back to this one. So here d lambda equal to 1. So in that case, it is enough to calculate the number of this element. So how many irreducible representation appears inside of that given n-tensor product representation? We need to calculate this number. This number is exactly equal to this combinatorics number. So in this way, this combinatorics number behaves as this way. So then we have this one. So this one is t minus 1 times log n. So this means that if the number of, parameter is t minus 1 or d minus 1, in that case, in the state IID case, what we have this one. So this is the number of parameter and half and log n. So this is a state estimation case. So you need to divide it by 2 for that coefficient. But now we don't need to divide by 2. This one is the number of parameters. Direct number of parameters times log n. So this means that this coefficient becomes twice as the usual case. So in this sense, we can conclude that this one achieved the Heisenberg scaling in the sense of the mutual information. Now we want to compare another case. Of course, t equal to case. This one is t minus 1 equal to 1. So quite simple. So and that optimal input state is this guy. It is enough to consider this one. Of course, you can consider that random permutation, or you can consider the decay state. So any kind of this kind of vector is okay to realize that this kind of optimal performance. But sometimes the people want to consider only the optimization mutual information. No. Optimization of the Fisher information. In that case, what is the solution? Optimum Fisher information can be realized by only this kind of state. This one is sometimes called the null state. In the case of null state, the mutual information is exactly equal to the log 2. Because we have only two states, the superposition of the two guys. So in that case, even though the considering the average, so the maximum mutual information log 2. So this is quite small. So this is quite worse than the that can compare with this guy. This guy realizes the optimum mutual information, and this one realizes a very bad mutual information. In this sense, clearly, how to say? This kind of the known state cannot realize the good global information. So, but many people want to realize this kind of state. So, but this is less informative. So, this is meaningless for the real state channel estimation. However, people always focus on this one. So, this is very bad for the wasting some resource. So, if you want to get the much resource, you need to realize this state. So this is a very confusing situation. But sometimes we have another case. Sometimes we need to minimize this kind of error. In that case, that optimum state is not this guy. We need to modify this coefficient. So in this sense, the optimal state depends on the some criteria. So now we consider the mutual information criteria, but if you consider that kind of square error criteria, we need to modify input state. But even though that kind of optimum state also have a very nice mutual information. And finally, we discuss the n-tensor product of the usual unitary representation. So in that case, we want to consider SUT. So and in that case, we have n-tensor product of this guy. So n-tensor product. So you have same unitary application, n copy of n unitary application. So in that case, you have that irreduced decomposition in this way, and this is multiplicity space n lambda. So and this is unitary irreduced component, and each depending on lambda, this is Young tableau. And depending on Young tableau, you have a reducible space, and its dimension is calculated by in this way. And this guy is upper bounded by this guy, and reference system is if sufficiently large, so you can calculate this guy, this square. So in that case, what we have, so the number of this kind of optimal performance is upper bounded by this one, and you can obtain this upper bound. And also, if we prepare this guy, so in that case, optimal this guy also behave to this one. So in this sense, we can find that the optimum mutual information is almost this guy, and this is not divided by 2. So if we consider the state estimation, in that case, and IID case, so we need to divide it too, but now we have this coefficient. So this is much larger than conventional case. So in this sense, this is quite efficient. So this I consider that we have a very nice mutual information if we prepare this state. And this is twice as a conventional case. So non-standard case. This is truly achieving the high-dynamic scaling in the sense of the mutual information. So we calculate the t equal to k, so we can exactly calculate each value. So in this case, we have this one, and in the case of the t equal to exactly we can calculate in this way. So we have some constant term in this way. So what is this? So now we want to consider Fisher information. Sometimes the Fisher information maximized. So in that case, what we have? it is enough to consider biggest irreduced component. In that case, biggest irreduced component is only this guy. And optimization of the Fisher information can be described only with one representation. This is enough. And that kind of dimension is this guy. So in that case, what we have, we have a mutual information of this one because we need to consider square of this guy and only one dimension. So please back to the previous one. No. So sorry. We don't need to do back. So we have a one irreducible decomposition, one irreducible space, and in that case, mutual information equal to the square of that dimension. So then log of square of this guy, then that square move to the here. So then mutual information calculated this way. And this one is only this one. So previously, optimum mutual information this guy, but if you optimize Fisher information, mutual information behave only this one, this one to this one. So this one is much better than this one. So in this sense, optimizing the mutual information is optimizing Fisher information is not so good in the sense of optimizing the mutual information. So then we want to close that it is quite important to focus on the mutual information, and of course in that case, how many distinguish elements. So in that case, in our method, we can distinguish this number of elements. So this is a distinguishable element. So this is quite large than the this kind of optimization Fisher information. So thank you very much. Maybe this is the conclusion. So anyway, so maybe I already discussed everything. So I want to close this one. So the conclusion is that Fisher information is not so good. So it is better to optimizing the mutual information. In the case of the channel estimation, at least the unitary estimation. So.
Yeah, thank you very much.
Yeah.
Nagoya, is there any question or comment? Yes, we have one.
Thank you for the talk. Why Fisher information is not so good? Could you explain some kind of intuition behind it?
Intuition.
Or like
Actually, Fisher information in the case of channel unitary estimation, we choose very bad input state. This input state is very nice only for the one specific point. So this is problem.
I see.
So, and also in the case of state estimation, still this is okay because we can use the two-step method. So why two-step method works well? So because we have our first estimation, and based on the first estimation, we can choose the second estimator. This is local estimator. But in that case, in the first step, the error is usual order of, if we focus on the variance or mean square error, the order behave as 1 over root n. So the first step has a 1 over root n. So and this one is something like the negligible. So this is not so bad. But in the case of channel estimation, unitary estimation, we have a Heisenberg scaling. So in that case, the contribution of the first part of error is quite essential because the order is different. So in the case of state estimation, the first error of the first part has some error behavior root n. So this part is sometimes like the negligible, not so serious. But in the case of channel estimation, of course, channel estimation has some conventional order is no problem. But if you want considering the Heisenberg scaling, we need to achieve the very higher order, 1 over n. So in that case, first estimation error of the first part is quite essential. So this part make a very bad effect. So then two-step method doesn't work. Of course, some people also consider adaptive method. Also, adaptive method doesn't work, I think. I didn't check this one, but we can easily find that optimum coefficient is cannot be attained. So because in order to attain, considering the global estimation, the most suitable method is group covariant method. We can exactly write down the optimal performance, and you can take its limit. That limitation has some coefficient, but that coefficient is always worse than the inverse of the Fisher information. This means that the Fisher information bound cannot be attained. So sometimes some people have some proof, but that proof does not work in the case of Heisenberg scaling. Because the order on the first part is not negligible in the case of the Heisenberg scaling. But people never check that proof. Only focus on the Fisher information. People want to enjoy the Fisher information.
Yeah.
But sometimes this is not so good. We need to careful about the whole proof.
Okay, thank you.
And how about from Shenzhen?
Small question.
Oh, no.
Okay. It's fine. Can you explain a little more about this multi-phase estimation, and you have this factor of 2 improvement? Can you explain it more? I could not get it.
Yes, this is multiple phase estimation. So multiple phase estimation case, the irreducible representation is one dimension because this is abelian group, so commutative group. So irreducible representation dimension is dimension irreducible space is one. So then it is enough to consider number of irreducible representation because we have this formula. This is one. So then it is enough to consider this number of different representation. That kind of different representation is described by this one. The total is n, and we have a n vector. We have a n vector. No. We have a t vectors, t basis. But we have an n tensor product. So in that case, we need to consider the combination of this one. This combination is can be easily calculated this one. So then it is enough to take this one. So this one can be expanded to this way. Sorry, I forget that. This one is recently published in the quantum. So you can find my paper in quantum. So he could understand. So
I see. Yeah, from the web page, our web page, there is a link to the full paper, I think. So please check. Any other comment or question from Shenzhen? Is it okay? Then let's thank Hayashi-sensei again.
thank you very much.
And
Okay, so now morning session is closed. So
yes.
In afternoon, maybe I will be a chair. So and
Yes.
we have several talks.
Yes. So see you in the afternoon.
See you. So I will close this one.
Yes, please.